So mathematicians learn polar form not just to convert arbitrary points in equations, they actually have a purpose. And the idea is that any mathematical idea that can be represented as a two-dimensional quantity can be represented in this polar form, and probably one of the more common and useful two-dimensional mathematical objects that we work with are complex numbers. By the end of today, we should be able to rewrite complex numbers into polar form, also known as trig form. And one thing that we can do to complex numbers when they're in these forms is to multiply and divide a lot easier. So let's refresh our memories on what complex numbers are. Complex numbers in standard form are defined as z equals a plus bi, where a and b are any real numbers. So complex numbers are those imaginary numbers, but they come in two parts, a real component, A, and an imaginary component, B. Now remember that we are able to actually plot complex numbers, and we plot them not on a coordinate grid, not on a Cartesian plane, but on a complex plane, or also known as an Argand plane. However, although the names are different, their structures are basically identical. Instead of having an xy axis, you have a real and an imaginary axis. So every single complex number can be represented as a coordinate. Hey, what we just learned in 8.1 and 8.2, anything that can be represented as a coordinate can be represented in polar form. So if I were to take a random arbitrary complex number, right? Say z sub 1 is, I don't know, I'm just making up some numbers here. I don't have this planned. 2 plus 3i. That says, or what that looks like is on a real number line, the real component is 2. So I'll go 2 tick marks. I'll just go ahead and draw all the tick marks here. On the real number line, I'll go to 2 spaces. And on the real, imaginary number line, I'll go to 3 spaces. So this location here is the location of the complex number 2 plus 3i. So notice it works 100% the same as rectangular coordinates in terms of the backbone, the infrastructure, even though conceptually it's a completely different concept. So because of that, it should have a polar form. Now we do have some slight variations in terms of vocabulary when we do polar form in the context of in the context of complex numbers. So remember how with regular coordinates we had an r, radius, and theta, angle. Well, if we're talking about complex numbers, the vocabulary changes. This distance, I guess I should use a different color. This distance here is not a radius, even though conceptually it could be. In the context of complex numbers, we call it the absolute value, or the argument of the complex number. And the angle here, yes, it is an angle, but it's called the argument, or the direction of the complex number. So, let me just go ahead and write this formally. In the context of complex numbers, the r is called the absolute value, or the modulus of a complex number. And the theta is called the argument. Right. But conceptually, the idea doesn't really change. The modulus is just the radius, it's the linear distance, and the argument is just the angle. And the formulas to find them are 100% the same. So it's the same bridges that connect polar coordinates to rectangular coordinates. But just for the sake of uniformity, for the sake of completeness of the notes, let's go ahead and build or rebuild those bridges. So without using specific numbers, for any complex number, let's call it z here, I know it has the structure a plus bi. What does that mean? That means this length here is a, this length here is b. So what is the bridge, or what is the algebraic connection between a complex number in standard form a and b with the modulus and the argument? Well, we can just see, just by visual inspection, that the modulus squared is a squared plus b squared. So that's the formula you would use to find the modulus. And we can see that the relationship between the standard form with the argument is a tangent. Tangent of theta equals b over a. So I guess this would be good information to have on your index card, but again, it isn't anything new. It's the same bridge, it's the same logic, except we call it by a different name because we're doing it in a different context. We're not talking about arbitrary rectangular coordinates now, we're talking about complex numbers. So converting polar form converting complex numbers from standard form to polar form is all about finding these arguments. Now, the other bridges, looking at the same picture here, we can see that a, since it's the adjacent to the angle, is going to be the modulus times cosine of the angle, and b is the modulus times the sine of the angle. So if I take standard form a plus bi and just do those substitution, we end up with modulus cosine theta plus modulus sine theta I. And notice how these guys here, they both have a modulus in common, so I can factor that out. We end up with this expression here. Now, mathematicians, we're lazy. We don't want to constantly write down this absolute value symbol all the time. So we just change it back to what we're familiar with as r. And that right there is what we call the polar form of complex numbers, right? So the polar, also known as the trig form, trigonometric, is merely substituting the algebraic bridges between rectangular coordinates and polar coordinates here, the bridges here, into the standard form of a complex number, and you end up with something that looks like that. So let's go ahead and write it out formally. Okay. Written formally, it says a complex number z equals a plus bi, that's in the standard form, has the polar form, also known as the trigonometric form, z equals r times cosine theta plus I sine theta, where r is the modulus. Now, let's go back to the bridges here. If the modulus squared is a squared plus b squared, then a single modulus must be the square root. And tangent of theta is going to be b over a. So if I want to figure out what the theta was, I would just have to take the inverse tangent. Right? Again, some vocabulary. R is called the modulus of the complex number, and theta is called the argument. So if I ask you, write your final answer, or convert this complex number to polar form, this is the structure. I guess I should not highlight the Z. This is the structure of every single complex number in polar form. It's sometimes called the cosine I sine form for obvious reasons. It's sometimes called the CIS form because C stands for cosine, I stands for the imaginary, S stands for the sine. So to convert it, we're not doing anything new. It's just what you did in 8.1 when you converted rectangular coordinates. The only difference is we're not converting an arbitrary location in space. We're converting a complex number. So if I asked you to write 1 plus I in polar form, right? Recall that polar form is R cosine theta plus I sine theta. In order to write polar form, we need to figure out what R is, and we need to figure out what theta is. So every single complex number is A and B. Do note that B is the 1, not the I. A and B are real numbers. So to do this, we need to figure out what R is. Well, it's Pythagoras' theorem. R is simply A squared plus B squared. So that's radical 2. Theta is such that if you take the tangent of it, it'll be B over A. So B over A is 1. So theta is tan inverse of 1. Right? Now remember, when you take an inverse trig function, you always have to be mindful of what quadrant you're in. So any answer I initially get, I'm going to consider him as my reference angle. So what angle has a tangent value of 1? Oh, I know that's going to be 45 degrees, pi fourths. Take a look at your original complex number. This is a positive 1 plus positive I, positive A, positive B. So what quadrant has positive reals and positive imaginary? You're in the first quadrant. So if you put your reference angle of pi fourths in the first quadrant, your actual angle will be the same, right? So there we have it. 1 plus I in polar form is R times cosine theta plus I sine theta. This is the polar form of the complex number. Now, I know it looks a bit more complicated looking, and I will agree with you. Why would anyone want to deal with this messy looking expression when this is nice, neat, in a concise package? We'll see its advantage later when we do multiplying and dividing. But let's do a handful more examples of converting just to make sure we get the idea. So let's get away from the first quadrant. Let's do something a bit more interesting. So let's say I wanted to convert, I don't know, negative 1 plus radical 3i, or I radical 3, into polar form. So again, to convert into polar form, we need to know what polar form is. It's R cosine theta plus I sine theta. So to convert into polar form, we need to figure out what R is, and we need to figure out what theta is. In this particular problem, A is negative 1, B is radical 3. So R is just Pythagoras' theorem. A squared plus B squared. Notice I always use parentheses to include any potential negatives. So that's 1 plus 3 square roots of 4 is 2. Theta is such that when you take the tangent of theta, it's always going to be B, which is radical 3, over A. So theta equals tan inverse of negative radical 3. I always like to use reference angles when I do inverse trig functions, so I ignore this negative. What angle has a tangent value of radical 3 over 1? That is going to be, 60 degrees, or pi thirds. But we have to be mindful of what quadrant we're in. Notice our original complex number is -1 plus I radical 3. So it's negative real, positive imaginary. So if this is the real, this is the imaginary. What quadrant do you have negative real numbers and positive imaginary numbers? That's going to be the second quadrant. So my reference angle of pi thirds is going to be in the second quadrant, which means your actual real angle is 2 pi thirds. So there we have it. Once you find r and theta, you have the polar form. So -1 plus radical 3i, I'll write it in the form that they like. According to our math, in polar form is 2 times cosine of 2 pi thirds plus I sine 2 pi thirds. This is the polar form of that complex number. So I think 2 examples is good enough. If after these 2 examples you're still confused, please let me know in class. Now the second lesson goal is to utilize these polar forms to do operations on them. Now, why would we want a different format to do something that we've already done before? We have already added, subtracted, multiplied, and divide complex numbers in previous units. Well, recall to multiply complex numbers in standard form, we use repeated distribution. Okay. For example, 2 plus 3i times -4 plus 4i. In order to answer this question, we would have to do this times that times that times that times that. Not necessarily hard, but sometimes can get messy. You might make little mistakes combining like terms, etc., etc. Dividing was even more hectic. To divide complex numbers in standard form, that's important. We multiply the numerator and denominator by the conjugate of the denominator. For example, if I want to divide 5 minus 3i by -1 plus 2i, you would first have to multiply top and bottom by the conjugate of the denominator. And then once you do that, you had to simplify the numerator and denominator separately. So dividing complex numbers in standard form was basically 2 of the multiplication problems in 1. Not physically hard. It's not really that complicated. It's just very tedious, lots of work. A lot of people made little mistakes when it came to multiplying, combining like terms, so on and so forth. Compare how simple multiplying, dividing complex numbers is in polar form. So we can actually, it's so simple that we can actually prove it, right? So in polar form, suppose we had 2 complex numbers. Say z sub 1 is r sub 1. It has its own modulus times cosine. It has theta sub 1 has its own argument plus I sine theta sub 1. And let's say we had another complex number, z sub 2. It has its own modulus and argument. So I'll use different subscripts. And let's start off with multiplying them, right? So let's multiply these 2 complex numbers. Then z sub 1 times z sub 2 is equal, well, if z sub 1 equals this guy and z sub 2 equals that guy, then when I multiply them together, it's simply this times that, right? So we have r, and in terms of multiplications, I like to move the monomials in front. So it's r sub 1 times r sub 2, and then the parentheses will multiply each other. And then the rest is just algebra. So if you go ahead and distribute this guy correctly, you got to be very, very careful. So that's what cosine theta sub 1, cosine theta sub 2, and this will be a plus, I cosine theta sub 1, sine theta sub 2, that's a plus, I sine theta sub 1, cosine theta sub 2, and then plus I squared sine theta sub 1, sine theta sub 2. Oof, running out of room there. Now we're going to do a little bit of fancy manipulations and factoring. Let's recall from, geez, I forget what unit it was. Was it unit 3? I think unit 3 is when we did complex numbers. I squared is -1, right? So that just means that this whole term here becomes a minus. Notice how these two terms here, they both have an I in it, so they go together. Once I change the I squared to -1, this doesn't have any I's, this doesn't have any I's, so we'll go ahead and put those together first. So this would equal the cosine, I guess I should keep the color codes. Cosine theta sub 1, cosine theta sub 2, and then it turns into from a plus to a minus because of the I squared here. So it'll be a minus sine theta sub 1, sine theta sub 2, plus, now because I recognize that this term here and this term here both have an I, we'll go ahead and factor out that I. And then what's left over is cosine theta sub 1, sine theta sub 2, plus sine theta sub 1, cosine theta sub 2. Well, that's a very interesting pattern. Right? We've seen this before. Right? This is cosine of the first angle times cosine of the second angle minus sine of the first angle, sine of the second angle. That is precisely the sum formula for cosine. We did this in Unit 7. That is precisely cosine of those two angles added to each other. Plus I. Similarly, we've seen this pattern before, except it's sort of backwards. Sine of the first angle, cosine of the second angle, plus cosine of the first angle, sine of the second angle. That's precisely the pattern for the sine of a sum. So this equals I sine of theta sub 1 plus theta sub 2. Right. What does all of this work say? All this work says is if you have two complex numbers and you wanted to multiply them and they are in polar form, oops, I forgot the subscript 2 here, then all you have to do is multiply their modulus together and simply add the angles. Now that is a heck of a lot easier than doing all this repeated distribution stuff, right? And that's sort of one of the advantages of polar form. It reduces multiplication into simply the sum of angles. That's precisely what, physically, what happens when you multiply by a complex number. It's just a rotation, rotation by the amount of angles that the complex numbers represents with some sort of scaling of the modulus. We can repeat the process for the division formula, but I'm not going to waste time on it. I think you guys get the idea. You literally do the same thing. Here's two generic complex numbers, divide them, and work out the trig identity. And maybe I'll leave that as an exercise for you. But let's go ahead and summarize everything. Right? Multiplication and division of complex numbers. in polar form. The official statement, the formal statement says, if z sub 1, let's how should I word this? If two complex numbers, z sub 1 and z sub 2, have the polar form, z sub 1 equals r sub 1 cosine of theta sub 1 plus r plus I, sine theta sub 1, z sub 2 equals r sub 1 cosine of theta sub 2, not 1's, 2, stop rushing, plus I sine theta sub 2. Then, if I wanted to multiply them, all you have to do is multiply the r's and add the angles. If I wanted to divide them, it's literally doing the exact opposite. You divide the r's, and you can probably guess what we do to the angles. Instead of adding the angles, we would subtract the angles. So this might be good to have on your index card. That is sort of the formula to multiply and divide complex numbers in polar form. Now, it looks like a very messy, complicated formula, but the idea, I hope, is very simple. To multiply complex numbers, multiply the r's, and simply add the angles. To divide complex numbers, divide the r's, and subtract the angles. Easy peasy. Okay. So let's just do a quick example. If, I don't know, z sub 1 equals, let's just make up some complex numbers in polar form. 2 cosine pi fourths plus I sine pi fourths. And z sub 2 is 5 times cosine of pi thirds plus I sine of pi thirds. Find their product and quotient. Specifically, I want to find z sub 1 over z sub 2. So look how easy and fast things are once it is in polar form. All right, so let's do the first one, z sub 1 times z sub 2. Well, even though it looks crazy, complicated, and messy, just remember what the formula says. You multiply the arguments, that's 2 times 5. And then for the angles, you simply add them. So it's pi fourths plus pi thirds. Plus I sine, the angles will always be the same. Pi fourths plus pi thirds. That's it. I multiplied it. Then all you got to do is simplify. 2 times 5 is 10. And pi fourths plus pi thirds have a common denominator of 12. So that's going to be 7 pi 12ths. That's it. That is the polar form of that. That is the product of those two complex numbers in polar form. Now, these parentheses with the angles are sort of superfluous. You don't need to write the inner parentheses if you don't want to. Dividing is just as easy, except instead of multiplying and adding the angles, you divide the modulus and subtract the angles. So it's 2 over 5 cosine of pi fourths minus pi thirds plus I sine pi fourths minus pi thirds. And then you just do math. So what's pi fourths and pi thirds? The common denominator is 12. So that is negative pi 12ths plus I sine. And this would be negative pi 12ths. Don't leave the negatives in there. Use the even-odd identities. So we know that a negative angle inside of a cosine does absolutely nothing. But a negative inside of the sine, you can pull out that negative. So it becomes a minus I sine pi 12ths. Right? So that we divided. Now, if the question asks you to find the product and quotient in standard form, then all you got to do is just break out a calculator, right? Take out a calculator, make sure it's in rating modes, and literally just type this in. Distribute the 10, type it in, and then you should get an answer in standard form. So if I were to type in the product in standard form, take out my calculator, what is cosine of 7 pi 12ths, and then multiply by 10, I get approximately negative 2.588. If I do the same thing with the sine, I type into my calculator sine of 7 pi 12ths, and then I distribute the 10, I get approximately positive 9.659, and of course has an I in it. You do the same thing for the quotient. You're going to get approximately 0.3864 minus 0.1035i. But just read the instructions. If it doesn't say put it in standard form, you can leave your answer in polar form. If it asks for standard form, obviously just take out a calculator. But that's it. That is one cool, neat application of polar form. It gives us a way to multiply and divide complex numbers fairly quickly, fairly easily, in my opinion. Multiplication boils down to multiplying the modulus, adding the angles. Dividing boils down to dividing the modulus and subtracting the angles. Good luck.